Assalamu alaikum. So in this video we will learn Kronig Penny model. So you will see that we have to go through a rigorous mathematics and calculations, right? But I will solve every line step by step and with details explanation. Okay, so let's start. So first let's talk about one single atom. Let's say we have a nucleus of a single atom and an electron at distance r, and we can write the potential energy of this electron is equal to minus 1 by 4 pi epsilon q, the charge of this nucleus, and the charge of the electron, let's say E, where E is 1.6 into 10 to the power minus 19. Just take the magnitude, don't take minus here, just only magnitude, okay, divided by r. So in this case we can say the magnitude of the potential energy is simply proportional to 1 by r, and again we can say that V is all the point negative, right, as you have a negative sign here. And again, if r is equal to 0, if you put r is equal to 0 here or r tends to 0 here, then V will become tends to infinity, and if you take r tends to infinity, then V will be tends to 0. That means you have these two things. Okay, now considering these things, let's draw a graph of V versus distance graph. And if you draw this graph, you will see that when r is tends to 0, b is tends to infinity, right? Actually not infinity, 1 by 0 infinity, and again you have a minus here, so I'm very sorry, you have to take a minus here, so minus infinity. Okay, so this graph will start from here, minus infinity, and as you will increase the distance, the magnitude of the V, as you increase the distance, the magnitude of the B will decrease, and it will decrease, the magnitude will decrease, and when r will become infinity, the V will tends to 0. So that means this graph will forever tends to touch this line, but it never can. Okay, so we can draw another graph to represent this phenomena. Let's say we have a positive charge here, nucleus here, and let's say this is the level where potential energy V is equal to 0, and that means from here, at infinity, the potential energy of the electron is 0, but as you go near the nucleus, it will become negative, right? Let's say here V is equal to 0, but as you go close to the nucleus, let's say here V is minus 5. Here let's say, just I am giving an example, V is minus 10. That means the potential energy is decreasing, right? Minus 5, then minus 10, so V is decreasing. Again it will increase, and its maximum value will become 0 at the infinity. Okay, so this is the scenario when you have a single atom, but in a crystal you will not have a single atom. So there you may have multiple atoms arranged in a regular shape. Okay, so if you have a single atom, you may obtain a graph like this, right? That means, let me draw a line here. If you have single atom, you may have let me draw this here, you may have a graph like this, and similarly for this atom you may have graph like this, and for this atom you may have graph like this, and similarly for this atom, this nucleus, you may have graph like this. But now as they are together, so at this point you can see that the two graphs are overlapping each other. That means here you will have the resultant, right? So let's draw this thing again, and you have to listen to here carefully, that at this region two graphs overlaps each other, so this graph will become like this. Again, as two graphs overlap each other, here the graph will look like this, similarly here look like this, and we can assume that here is another nucleus, here is another nucleus. So in this point also the graph will look like this. Okay, so that means we have a periodic arrangement of potential energies, right? These are all the values of potential energies. Here is higher, then again lower, then lower to higher, then again lower. These are representations of potential energies. Okay, so now starts the Kronig Penny model. Now what Kronig Penny model, let's see what Kronig Penny model tells us. Okay, so Kronig Penny model tells us that instead of this periodic oval shape or this type curve, we will make our calculation simpler. That means we will let's say this axis is v and this axis, let's say x, and at this point, let's say at this point x is equal to 0. Here let's say x is equal to a. At this point x is equal to negative, that means minus b. Here a plus b, and here let's say minus a plus b. Okay, so at the first region, at this region v0 will be equal to 0. That means the potential energy will be equal to 0. But from a to a plus b, the potential energy, let's say, becomes v0. Okay, then again at this point the potential energy will be 0, and again it will become v0. Similar thing happens here. At this region the potential energy is v0, again 0, then again it will becomes v0. And this is a easy case, and we can easily apply a Schrodinger equation in this scenario. Okay, so let's apply a Schrodinger equation in this case. So let me first tell you that according to Bloch's theorem, Bloch's theorem says that if we have this kind of potential, this kind of periodic shape, then the wave function psi x will be equal to ux e to the power j kx shape. That means the wave function will be like this shape. Okay, so accepting this theorem, let's apply this thing in the time independent Schrodinger equation. So let's apply this thing time independent Schrodinger equation. So what is the time independent Schrodinger equation? This is simply is equal to delta square psi by delta x square. Oh, one thing, we are working with one dimension. Okay, you have one dimension only x. Okay, so we have to write the one dimensional equation. Then 2m divided by h bar square E minus v is equal to 0 is the energy of that particle, and b is the potential energy. Okay, so now we need to put this psi x here, and again we have a psi here, so again we need to put it here. So first of all, let's differentiate psi with x, and then we will again differentiate it. So if I differentiate this thing, so I will get ux. Don't differentiate ux, just now differentiate e to the power jkx. So if I differentiate the second term, I will get like this. And now I will differentiate the first term, so delta u by delta x, and I will don't differentiate the second term, so e to the power jkx. Okay, so now I will again differentiate this term. So I have two terms here. Let's first differentiate the first term. Okay, so let's start. So again, let's don't differentiate ux, just differentiate the second term. Then we will get e to the power jkx into jk, and we have another jk here, so let's write it here. Then again we will write the second term, e to the power jkx into jk, and we will differentiate the first term here. That means delta u divided by delta x. Let's not write the ux here. Okay, so now let's differentiate the second term. So if I let me check again. Okay, so let me differentiate this term. If I differentiate the first term, I will get delta square u divided by delta x square, and let not differentiate this term, so e to the power jkx. And now if I don't differentiate the first term, then I have to differentiate the second one, so e to the power jkx into jk. Okay, so now let me take common. What you will see that we have e to the power jkx, 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 e to the power jkx. So let's take common e to the power jkx. Then we will get here ux. Let's don't write ux, let's write just u. Okay, we know that u is the function of x. Okay, so u. Now j square is equal to -1. Then you have here k square, right? And then again jk, you have, see, you have jk delta u by delta x, again jk delta u by delta x. That means 2jk delta u divided by delta x, and then you have only this term, so delta square u divided by delta x square. Okay, let me check this with my note. Let me rearrange this term. So I will have delta square u divided by delta x square, then 2jk delta u divided by delta x, and then minus k square u. Then we have a common here, e to the power j kx. Okay, so now I will put this value here, right? So let's do this. So delta square u divided by delta x square, 2jk delta u by delta x, minus, let me put this thing here. Then we have 2m divided by h bar square, 2m divided by h bar square, e minus v, and then we have a psi, right? And what is psi? Psi is equal to ux e to the power jx according to Bloch's theorem. So let's, instead of psi, let's write here ux, then e to the power jkx is equal to 0. So e to the power jkx, e to the power jkx cancels out, and again e to the power jkx, e to the power jkx cancels out. Then we have a equation like this. Okay, so now we have two types of regions, right? So we have two types of region. In this region, the v is equal to 0. Here v is equal to 0. So first let's take this type of region, so where v is equal to 0. Okay, let me draw this again so that you can understand it. Okay, so this is a and this is minus b. Okay, so we are working with where v is equal to 0. Okay, so that means should I rearrange this equation again? Okay, I think I don't need to rearrange this equation again. Then I will get delta square u delta x square plus 2jk delta u by delta x. Now let's do one thing. This v is equal to 0, right? So minus k square u, then plus 2m h bar square e, as v is equal to 0. Okay, so now let's take 2m divided by h bar square is equal to alpha square. Let's assume this thing, that 2m by h square is equal to alpha square. You have to remember this thing because it will be useful later. Then we have equation like delta square u divided by delta x square plus 2jk delta u by delta x. Then if I take this thing, we have a e here also, so this is alpha square, then minus k square minus alpha square u is equal to 0. So this is our first equation. Again, where v is equal to v naught, we will get another equation, right? And now let's assume that from this equation, let's assume that 2m, I mean this term, I assume that 2m e minus v divided by h bar square. Now let's assume that this term, this will be equal to beta naught, right? As when v is equal to beta naught, so this will equal beta naught. This is equal to beta square. Okay, so let's write beta square in this equation, and we will get delta square u divided by delta x square plus 2jk delta u by delta x, then minus this term minus k square, then this is beta square, right? So let's write it here and take u common here. So this is our second equation. So I haven't write one thing, that the u here at this region, let's say it's the first region, and let's say this is the second region. So at the first region, let's say u is equal to u1. Here you have u1, and this is also u1. And for the second region, where v is equal to v naught, u is equal to u2, u is u2, and here you have to take u2. That means from these two differential equations of second order, you will get u1 and then you will get u2. So let's solve one equation and you will understand another equation by yourself. Okay, so let's first work with the first equation. Okay, that means this equation. So if I work with this equation, so do you know how to solve a second order differential equation? Let me tell you that I have to put delta by delta x. I have to put, let's say, lambda instead of delta by delta x, and again I have to put delta square divided by delta x square instead of, I have to put lambda square instead of this operator. So let's put that here, lambda square u plus 2jk. I have to put here lambda u, then minus k square minus alpha square u is equal to 0. It's u1, right? So you will see that u1 cancels out, and now we have to find lambda. So here we have a quadratic equation, right? And the formula is minus b plus minus b square minus 4ac divided by 2a. So let's find lambda. So minus b is equal to minus 2jk plus minus b square. So 4jk square, that means minus 4k square. then 4 into a is 1 and c is equal to minus k square minus alpha square. Okay, so this minus and this minus will become plus here, then here 2 into a. Okay, so this minus 4k square and this plus 4k square cancels out, and we will have minus 2jk plus minus 4 into alpha square, minus 4 into alpha square. Let me write it clearly. We will have minus 4 into alpha square. That means minus, what does it mean by minus? Minus means j square, right? Okay, so let me take root here, then I will get minus 2jk plus minus j 2 alpha divided by 2. Now 2 cancels out, and finally I will get what I will get here, I will get two things. So minus jk plus minus j alpha. So I have two lambdas here. So one is minus jk plus j alpha, and another is minus jk minus j alpha. That means j alpha minus k, and another is minus j alpha plus k. Okay, so I have here 2 lambda. Let's say this is lambda 1 and this is equal to lambda 2. So what I was doing, I was trying to find u1, right? So I was intended to find u1. So u1 will be equal to, I have to write constant here, two constants, then I have to write here e to the power lambda 1 and here e to the power lambda 2x. I don't know what is a. I will find it, I can find it by some boundary conditions. So lambda is j alpha minus k, lambda 1 is j alpha minus k, and here minus j alpha plus k. I am forgetting to put here x. Okay, so this is our equation for u1. So this is our first equation, and similarly if you compare these two equations, you will see that these two equations are similar, right? These two equations are similar. Just the difference is here you have alpha square and here you have beta square. That means to find u2 you have to write just beta instead of alpha. So if you want to write u2, just you have to write beta, instead of alpha. Again you have to write beta instead of alpha, and you have to write here another constants. Let's say it's c and it's d. Okay, so you have these two equations. Now using these two equations you will make a condition for which these two equations will satisfy. These two equations, the value of a, b, c, d will exist. You will have a conditions, you will make a conditions. So let me take a break now. Is this video becoming too long? Let's see how much time. Already 24 minutes, right? So this is a very long video, I guess. Okay, no problem, as I am doing all the thing in details by hand, so it will take some time. Is all right. Okay, so now let's proceed. Let me draw that graph again. So it's our v and a, and it's minus v. So for this region we have a potential energy V naught, but here potential energy is 0, and here again is V naught. Okay, so I have two regions, right? This is first region and this is the second region. I should draw this graph some bigger. Okay, I don't need it, I can zoom it. Okay, so first of all as psi, the wave function is continuous, right? Continuous, that means it's not possible that just left of this point, let's say psi is equal to 2, but just here psi becomes 3. No, it's not possible. As psi is continuous, that means psi, if at this point psi is 2, also at this point psi will become 2. That means we have that this is the x-axis, and at here x is equal to 0, right? That means at this point we have to maintain the continuity of psi x. That means at this point u1 0 is equal to u20, right? As psi x is equal to ux e to the power j kx. Can you remember this? As psi is continuous, that means u might also be continuous. So we can write this thing that u10 is equal to u20 at for this point. So if I write x is equal to 0 here, I will get a plus b, and if I put x is equal to 0 in this equation, I will get c plus d, as e to the power 0 means 1, e to the power again 0 means 1, e to the power 0 1, e to the power 0 1. So I have an equation like this: a plus b minus c minus d is equal to 0. Let's make it number 1 equation. Okay, as I have used number 1, okay, let me forget the previous thing. This is the equation which I mentioned, number 1. Again we can use this continuity equation right here, right? So at this point, let me check my note here. 1 minute please. Okay, let me do another thing. Okay, so let me do another thing. At this point x is equal to 0. Oh, what's wrong with my notepad? I don't know what's wrong with my notepad. Let me pause this video and check that again. Okay, so I think my there was some problem in my notepad. Now it's okay. Okay, I have to do another thing. At this point, as psi x is continuous, another property we have, that another property is delta psi by delta x is also continuous. That means the right before left, just at the left point of s is equal to 0, we will have du by dx at 0. Oh, sorry, let's say this is d delta u1 by delta x at 0 will be equal to delta u2 divided by delta x 0, right? That means now we have to differentiate u1 and then v1. So let's differentiate u1. Okay, so if I differentiate this thing, I will get a e to the power j alpha minus kx into alpha minus k, right? Yes, and then if I differentiate this term, I will get b e to the power minus j alpha plus k, and again I will have alpha plus k. Okay, now if I differentiate the second u2, I will have C e to the power j beta minus k, then beta minus k. And now if I differentiate this thing, the second term of u2, then I will get d e to the power minus j beta plus k, and then again minus j beta plus k. I think I made a mistake here. I didn't write j here and minus j here. That means I will have a minus here also, and similarly here minus j. That means let's take this minus here. Okay, and now let's take delta u1 at 0 and delta u2 by delta x at 0.0. So if I take x is equal to 0 here, so I will get a j alpha minus k, and even again if I take x is equal to 0 here, I will get minus b j alpha plus k. Now if I take x is equal to 0 here, I will get c, I have a j here, so j beta minus k, and again I will have d, I will have x here, so d j beta plus k. So j cancels out, and finally I will get alpha minus k a, then alpha plus k b, then beta minus k c plus beta plus k d is equal to 0. Let me check this thing. Okay, so let me make this as second equation, and now we have successfully worked with x is equal to 0. Now let's move into some other point. Let's say now take this point in account. So let me now draw that thing again with some bigger shape. So I will get like this. So this is a and this is b. So and this is x is equal to 0. Oh sorry, actually this is a. Okay, so now we want to work with this equation at this point, right? So that means here you have, this is the first region and this is the second region. Now and this is the also second region, right? As we are taking that where v naught potential energy is v naught, we are taking that as second region. That means here you have u2, and at this point at this region you have also u2. Okay, now let's look at a. So at this point, just left side of a, the with the u is simply u1, but at the right side of a, simply you have u2, right? Now listen to me carefully. As this thing is periodically arranged, that means the value of this point is also equal to the value of this point. You understand why? Because this is periodically arranged. The potential energy is periodically arranged. That means at this point the value of u2 is equal to the value of u2 at this point. That means let's say u1a simply is equal to the value of this point, and this point is actually equal to the value of this point. That means minus b. So let me tell you again, as u is continuous, that means at this point the value of u1 is equal to the value of u2. But as this is, the potential is periodically arranged, and so u2 is also periodically arranged. That means at this point the value of u2 is equal to this point, right? So u1a is equal to u2 minus b. So if I do that thing, if I put a on my equation, I will get a e to the power j alpha minus k a. Instead of x, I have now put here a. Then b e to the power minus j alpha plus k. I have a x here, but instead of x, now I will put here a. Then again c e to the power minus j beta minus k a. Then d e to the power I think I don't have a minus here. I think I have a plus here. Okay, then minus j beta plus k a, right? Now let's take these things at the left hand side. Then I will get a minus here, I will get a minus here, and finally I will get a 0 here. So this is my third equation. And again, if I take the same thing, delta u1 by delta x at a and delta u2 by delta x at point b, if I do the same thing and put this value here, I have already differentiated these two functions, so I will again get a value here, right? So let me write the thing: alpha minus k a e to the power j alpha minus k a. Oh, I think you are getting bored, right? So pause this part, let me finish writing this thing. B e to the power minus j. So skip this part and go where I have finished this writing. Then beta plus k d e to the power j beta plus k. So this is my fourth equation. Okay, let's talk about a very important thing. So become ready. Now we have to talk an important thing here. See, I have three equations here. And what was our goal? Our goal was to find a, b, c, d, right? And let's see what happens. So to find a, b, c, d, we have apply our boundary conditions. So here you have a, b, c, d and their coefficients 1, 1, minus 1, minus 1. Again, you have find an equation with the coefficients of a, b, c and d. Here you have find the coefficients of a, b, c and d, and again here you have coefficients of a, b, c and d. So to solve this equation, you can make a coefficient matrix, right? So you can make a coefficient matrix. So you can make a coefficient matrix here. So those you are aware with how to do matrix calculation, you know that you can write here a, b, c, d, and at the left hand side you have to write the coefficient. Let's say at the first equation you have 1, 1, minus 1, minus d. So 1, 1, minus 1, minus d, minus 1. Then for the second equation you have alpha minus k minus alpha plus k. So alpha minus k minus alpha plus k, and so on. And you have a third equation, you have to write those things here. And you have fourth equation, you have to write those things here. And at the right hand side, see, you have 0, you have 0, you have 0, and you have 0. That means at the right hand side you have 4 0. That means it's an homogeneous equation, right? That means this system is homogeneous as you have 0 at the right hand side. And now let me tell you one thing from linear algebra. So from linear algebra concept, we know that if this coefficient matrix, if the determinant of the coefficient matrix, if the determinant of this coefficient matrix is 0, then you will get a value of a, b, c, d. That means you will get a non-trivial solution of a. That means you will get some non-zero value. You will get some non-zero value of a, b, c, d. But if determinant of this matrix is not 0, then you may get a, b, c, d all is equal to 0, or you may get a system where you have no solutions. That means the system has no solutions. But if determinant of this coefficient matrix is 0, then you will get some kind of value of a, b, c, and d. That means you will get a non-trivial solution if and only if the determinant of this coefficient matrix is 0. So this is a rigorous process to find the determinant of this matrix. So you can try by your own, but to save the time, I just write the final result here. So if I take determinant of this coefficient matrix, and after solving that determinant, I will get minus alpha square plus beta square, then 2 alpha beta sine alpha a sine beta a. Do you remember what was alpha and beta? Okay, let me write this equation and then I will make you remember. And then I have cos k a plus b. Okay, so let me make you remember what was alpha square. It was simply 2me divided by h bar square, and beta square was equal to 2me divided by h bar e minus v naught, right? And what was k? K was, from where we get k? Do you remember that we write psi x is equal to ux then e to the power j kx? So we get this k from here, right? Okay, so what I have written here, so this is the condition. And what is this condition? This is the condition for a, b, c, d will have a non-trivial, that means a non-zero solution. Maybe 1 or 2 may become 0, but it is but not all the values of all a, b, c, d will become 0. That means you will get some value of a, b, c, d. That means where is a, b, c, d? Here. Your goal was to find u1 and u2, right? That means if you will have some value of a, b, c, d. That means this a, b, c, d will not become 0. You will get some kind of value of a, b, c, d. Okay, so now, so that means to get some kind of value of a, b, c, d, the condition is this. So we have to maintain this condition. Okay, now let's take one case. Let's take one case. Let's say that v is tends to 0 and the potential energy v naught is tends to infinity. What does it mean? I mean, if you remember that I have this kind of periodical arrangement where the where this is minus b and this was v naught, right? Now let me tell you one thing. What am I now going to do? Now I will make b smaller. Oh, I'm sorry. Oh, okay, no problem. Let me do it again. So what now I will do, I will make again. Okay, let me try it again. Okay, Bismillahirrahman. Okay, let me explain it in another way. Again, there is some problem with my notepad. I don't know what is the problem. Okay, so let me tell you one thing. So this is v naught, then again 0, then again v naught, right? If you remember, this was our pattern. And now we will make b small. We will make b small and we will make v naught large. That means now b will be small and v naught will be large. Wait, that means after that the v will be small and b naught will be large. Again we will make b small and b naught will be large, but we will take b into b naught same. Okay, that means we will take b into b naught same. That means the b into b naught here and the b into b naught here and the b into b naught here is same. So what is b into b naught? The width of this rectangle is v and the height is v naught. That means the area of this rectangle is b into b naught. Again, the width is b and the height is b naught. That means the rectangle's area is b into b naught. Again, the rectangle's area is b into b naught. And after making b small and b naught large, at one point I will get that this width b is tends to 0 and the potential energy will become infinity, but the rectangle's area b into b naught will remains the same as previous. That means this b into b naught is finite, as b into b naught is finite here and finite here. That means although v naught is infinity, b tends to 0, but b into b naught is finite. So in this case, what will my that periodic arrangement looks like? Let's see. Then I will get here, I will get a pulse here, kind of delta function here, then I will have 0, then again I will have a delta 0, then the potential is 0, then again v naught will become infinity, and this will goes on and goes on. And let's see in this case what will happen. Okay, so let me write the equation again. Minus alpha square plus beta square. Okay, let me write it later. Let me first work with some conditions. So here b naught is infinity, right? That means E obviously less than v naught. It's many less than v naught, the energy of this particle. That means beta square is equal to 2m divided by h bar square E minus b naught. As E is negligible, so we can take E negligible in respect to v naught. Then I will get 2m v naught divided by h bar square. Wait 1 minute. Okay, so why I have do this? Because if you remember that in our equation we have sine beta b, right? So let's work with sine beta b and let's see what happens. Let's work with sine beta b. So sine beta b is equal to sine beta from this equation is equal to minus 2m. Okay, let me write it like this, that sine beta b, let me divide it by beta b. Wait, I have a call. Okay, so let's do this. So what I have done that is sine beta b, so I have to write here sine beta b, then I will divide by beta b and again divide by beta b, and as beta b okay, let me write one thing. Let's write beta b here, and sine, what is beta? Beta is equal to minus 2m v naught divided by h bar square, right? And then we have here b, so let's write b is equal to root over b into root over b. I think no problem here. And let's take this root over b, inside here. Okay, so if you remember that this beta b naught, so this beta b naught beta is finite, right? Is finite, that means this term is finite, but b is tends to 0. Similarly, at the denominator I will get the similar thing, as beta b is equal to this, so at the numerator I will get the same thing, 2m b naught b divided by h bar square, this thing. Okay, now as b is tends to 0, we know that sine x divided by x, where x is tends to 0, it simply becomes 1, right? So that means as b tends to 0, so this whole term will become tends to 0, this whole term will become also tends to 0. That means if you take the whole term tends to 0, you will simply get here 1, right? So I have obtained sine beta b. I have obtained that sine beta b is equal to beta b. So it's another property, right? Sine, if beta b is small, then we can write sine that angle is equal to just that angle. Okay, let me forget the thing. Let me just make a formula here. Okay, so now let's put that in my equation. My equation was alpha square plus beta square, then 2 alpha beta. Then we had sine, if you remember, sine alpha a. Then I had sine beta b, then cos alpha a, cos beta b, then cos k a plus b, right? So as b is tends to 0, so cos 0 degree means 1, and as b is tends to 0, so let's write here cos k a, and we found that sine beta b is equal to beta b, right? So it's equal to beta b, so sine alpha a, and here we have here 2 alpha beta, so beta cancels out, and okay, so another thing I have forgot to say one thing, that here you have alpha square plus beta square, right? Let me now tell you one thing, what will happen here, what will happen to alpha square plus beta square. So as we know that alpha square is 2me divided by h bar square, and we have obtained that beta square is equal to 2m divided by h bar square e minus b naught. So as b naught is infinity, so e is so small, so take it as negligible, so minus 2m h bar square b naught. So beta square is equal to minus 2m by h bar square b naught. That means beta square is tends to minus infinity, right? Beta naught is infinity and you have a minus here. Now tell me that minus infinity, let's 5, let's take a number 5, then minus infinity, what will be it? It will simply minus infinity, right? That means let's take that minus infinity is equal to beta square, and let's take for the moment that alpha square is equal to 5. So alpha square plus beta square will simply is equal to minus infinity, that means beta square, right? So we can take alpha square is so negligible, so that means we can take the effect of alpha square is so negligible, though it is positive, the effect of alpha square is negligible. That means here you have alpha square plus beta square. If you neglect alpha square, you will have beta square here. So if you now let's take this, now let's write the equation of beta square, then you will have 2 minus 2m. So what is beta square? Minus 2m b naught divided by h bar square. Then let's write here 2 alpha, then you have here sine alpha a, then you have a b here, right? So let's write here b, and now you have a cos alpha a here, so write here cos alpha a, and then write here cos ka. Okay, so now 2 cancels out, minus and minus become plus, so m v naught, so m v naught b, then at the numerator h bar square, let's write this alpha here, sine alpha a divided by alpha, then let's take another a here, so we have to write a here so that alpha a and alpha a matches, and then we have to write cos alpha a is equal to cos ka. Now if I write this term is equal to p prime according to the Neumann's book, Semiconductor Physics and Devices, Donald Neumann, so I will get p prime sine alpha a divided by alpha a plus cos alpha a is equal to cos ka, right? So this is my condition, so don't be lost. What is my condition? What these conditions tell me? That these conditions tell me that okay, let me revise this thing. Let me revise the whole thing, then you will understand it. So first we work with single atom, then we work with this multiple atoms in crystal, and then Kronig Penny model we take this simple model, and then we find two equations of u1 and u2. So I have told you that we will get a value of a, b, c, d, a non-trivial solution of this matrix. We have obtained a matrix here. So if the determinant of this matrix is 0, then we will have a non-trivial solution. That means we will get a value of a, b, c, d, and the condition for a, b, c, d will have non-trivial solution is this is the condition, and for this condition, if we maintain this condition, we will get this. Now listen to me carefully. Here you have alpha, and now we have to think that alpha is related to who, right? So then we take b naught is equal to 0, b tends to 0 and b naught tends to infinity, but we take bv naught same, bv naught same, bv naught same, that means finite. And if I take this thing, I will get a periodic function like this. And then after some calculation, I find that I have another condition, and this is the condition when b is tends to 0, b naught tends to infinity, but b naught is finite. And it is the condition for a, b, c, d have non-trivial solution. Okay, so this is the video. And one thing that you have to understand that alpha is related to E, right? Because alpha square is equal to 2m E divided by h bar square. That means the total energy is related to alpha square. So you will understand in the some next video that you will see that at the next video. Okay, so let's make this video end here. Thank you.